this one multiplied, x minus by x inverse should be identical, right? But this inverse, inverse 2, inverse 3, multiply 1, 1, the result is inverse 5, negative 5, right? Not 1. So something is wrong. You know that 2 by 2, like it is matrix, the inverse is 对角线互换，然后这个另外一边换符号，对不对？我记得是这样子嘛，对不对？所以你看这很显然是错的，这是错的，对。我还要除上它的比针，要除上比针，但是 anyway 这个一看就知道是错的，所以这边让大家知道说这个有点问题，但是concept is just like that, okay? Maybe like computation, for computation, I think you can do it yourself. But I mean, again, let me repeat. If I were you, and I see this question, I would just do it directly. Okay, I would not like do like diagonalization and then do it this way. Like, it does not make sense. It doesn't make sense to do it this way. But the following makes sense. Exponential matrices. According to Taylor's series. 你知道泰勒展开式？对不对？泰勒展开式，你们学过泰勒展开式 ？Okay. So e to the power of x equal to 1 plus x plus, s squared divided by, like factorial 2, okay? And x cubed divided by factorial 3 and so on, okay? Because it's infinite series. So for any n by n matrix A, EA is going to be given by similarly, okay? Using, you can express it in the exact same way, like okay, so if A is diagonizable, okay, then we can write that the A to be x inverse, okay, and then EA will be x times e to the power of e times x inverse, okay. This one, okay, e to the power of e is going to be this one. For this one, yeah, you cannot compute directly, obviously, right? Because it's an infinite series. Okay, so yeah, I mean the diagonalization is necessary in case like this. And an example here. If you want to compute e to the power of a, where a is like that. So first, like the eigenvectors will be -2, 1, and lambda 1 is 1, and negative 3, 1, lambda 2 is 0. So x is like -2, 1, negative 3, 1. Okay, and x inverse is right. It's still wrong. It's still wrong. But the counter, I think x inverse is wrong. X is correct if the eigenvectors and eigenvalues are correct. Then the x is correct, but x inverse is wrong. Okay, but you get the idea. I think this is like pretty straightforward. Okay, I mean, so this type of question will be a reasonable question to ask in the quiz and in the final exam, right? First, you are forced to use diagonalization. Okay. Second, it's not too complicated to compute. Okay, so to be honest, a lot of time it doesn't take a lot of effort to guess like what kind of question could appear in the exam or in the quiz, because I'm not the one who will give you like to compute like the determinant of like a 4x4 matrix or even like 5x5 matrix. That doesn't make sense. As long as you get a concept, we are in computer science. I mean, we can easily write a program to do it like to have the computer to do it. Okay, so the concept is important, but not the computation. Okay, so I usually do not give you like a question that takes a lot of time to compute. Okay, but yeah, I mean, for 2x2 matrices, I mean, it's usually not that much difficult to compute. Okay, no matter what you want, we need to compute. Numerous like determinant, everything. But you get an idea. Okay, so this is like how you can compute like the e to a power of a matrix. The last one is actually application. Okay. So a stochastic process is any sequence of experiments for which the outcome at any stage depends only on chance. And the Markov process is a stochastic process with the following properties. First, the set of possible outcomes of states is finite. Okay, there are only finite number of states. Second, the probability of the next outcome depends only on the previous outcome. Actually, this is the first order Markov process. The Markov process can have like a higher order. In other words, it can depend not only on the previous outcome, but also by the outcome of like previous ones. But anyway, we usually discuss the first order, so the outcome depending only on the previous one. Okay, the last one, properties are constant all the time. So these three rules, if they, help you to understand Markov process. Okay, actually, Markov process is something we use a lot in the analysis. Okay, for example, like some of you may in the future maybe like will take like machine learning, okay, and deep learning, these type of courses that we expecting like to learn how to predict the future, right? Okay, but there is a technique called a hidden Markov model, HMM, okay, which can theoretically help you to predict like a certain outcomes already, and that's like a tool that has been used like a long time ago in statistics and mathematics. Of course, that's based on Markov process. Okay. So anyway, so it is a good idea to understand Markov process. So vector is called a probability vector if all its entries are non-negative, because we are talking about probability, right? So all its entries are non-negative, and the sum of its entries is 1. Okay, because if you add up all the probability of all the possible outcomes, the result should be 1. Okay, 100%. Okay, so then here's an example. Okay. Blue, green color blindness. Like this is like an example, but I couldn't find like a concrete description for this question. But this question is you can easily see that people who are colorblind. Okay, so some people are colorblind for blue color. Some people are colorblind by green color. Okay, so say if you see we have these two statements, x1 equal to x1 1 equal to x2 0. It means let's say x1 represents blue color blind, x2 means green color blind. Okay, so this means that and 0 means a previous state. 1 means like superscript 0 means a previous state. 1 means superscript 1 means like next state. So that means like if a person has a green color blind, then its offspring, his offspring is going to be blue color blind. Okay, and if a person or put it another way, okay, if a person is blue color blind, its parent must be green color blind. Okay, if a parent is green color blind, okay, go to the second formula. I mean, there's a half chance its parent is either blue color blind or another half chance that the parent is green color blind. Okay, and you can represent this is market process because the next state depends solely on the previous state, and this probably will not change over time. So you can represent this as this one, the matrix form. Okay, and then obviously you get an A like this. Okay, and if you want, so this is market process, right? So what we care is, after like many generations, what will be the outcome? What will be the outcome if we know like this market process? Because like the first generation is going to be, say this is like the current state. If the current state is x, the next state is ax, okay, and the next state obviously is a times ax, right? So which will be x squared x. Okay, so if after many generations, okay, what will be the outcome? The result. So we care about A, we can say A infinite. This is what the result we care about. Okay, in the long-term future. Okay, after so many generations, what is the distribution of like this color blindness, where X is the initial condition. Okay, so it's like this. So first we can, again, diagonalize A. So we represent A as like this one. Here, one. Yeah, I think this one is correct. This one is correct. You see, exchange this and then change the sign, and then divide it by the determinant. So that's correct. This is X. This is X inverse, and the eigen. This is eigenvector 1, 1, negative 2, 1, and the corresponding eigenvalue is 1. Okay. So when you have like n to the power n, if you enlarge this and what happens like this one, this and this one you only have one copy, but this one gets the power of this one gets increased. But this it means that this one will keep there without change, but this one will eventually vanish. Okay, when n becomes like very very big, obviously, because this is like smaller than 1. Okay, so what happens is like we multiply this one with 1, 0, 0, 0, and the result multiply this one. So that's and multiply the initial condition. So this is the result. Okay, this is the result. So given an initial condition, you can predict in the long-term future, what is like a blue color blindness and green color blindness like distribution. Okay, so this is like a market process. Okay, which happen to have some connection to with the matrix diagonalization. Okay, so from here we learn something. Okay, if a marker chain with an n by n transition matrix A converges to a steady state vector X. Okay, then first X is a probability vector. Okay, it must be a probability vector. Okay, I mean no matter how you multiply it, okay, X is always a probability vector. Okay, that's for sure. Second, lambda 1 equal to 1 is an eigenvalue of A, and X is eigenvector belonging to lambda 1. So this is not like you see, when n become like a very large, okay, this one will stay to be 1. This one vanish. So in other words, so only this eigenvector matter. This one is not important. This one vanish. Okay, so that's like the idea of this theorem. Okay, the lambda 1 equal to 1 is the eigenvalue. Okay, and the X is eigenvector belonging to lambda 1. Okay, if it converge to a steady state. Okay, you see, it is impossible. Okay, for everything to vanish. if everything vanish, okay, I mean, the multiplication result is going to be 0. Okay, what does that mean? What that means, like, you know, your x is no longer a probability vector. It's going to be 0, 0, right? But it's not possible. Okay, so pretty much like for market chip, if there's a steady state, okay, you must have lambda, okay, to be 1. Okay, so if lambda 1 to be 1 is the dominant eigenvalue of a stochastic matrix A, then the market chip will transition, with transition A, will converge to a steady state vector. So this is, well, because like when n become large, all the eigenvalues smaller than 1, you know, the absolute value of eigenvalue smaller than 1 will vanish. So only one that's left is 1. So that's it. So that's like something we can learn, we can conclude from the market process. Okay, and we are pretty much done with this section. Okay, section 3. Okay, and then we will officially enter this section 4, which begin to no, we are going to start talking about like the matrices, which whose elements are complex numbers. Okay, so it has become more and more complicated. But